As we have already studied about degrees of freedom for a particular type of gas, here we are going to discuss about degrees of freedom for a gaseous mixture. As we all know, when substances are mixed at same temperature, we know well that no heat exchange takes place. This we already discussed in the topic of calorimetry, that when substances are at same temperature, these are said to be in thermal equilibrium, and if these are mixed, the temperature remains same. Say if n gases are mixed, say which are having degrees of freedom F1, F2 up to Fn, and moles we take N1, N2 up to Nn. That means for n gases, first gas which is having F1 degrees of freedom, N1 moles are taken. For the second gas, if it is having F2 degrees of freedom, N2 moles are taken, like this. And if these are mixed at same temperature, or even if these are mixed at different temperature, finally when thermal equilibrium is achieved, the temperature will be same. So we can state that total sum of internal energy of all the gas molecules will remain same, whether it is calculated mutually or independently. Like if we talk, if FEQ is the equivalent number of degrees of freedom for the molecules of mixture, then internal energy of mixture at temperature T we can write as FEQ by 2. Total number of moles are N1 plus N2 up to Nn RT. This is the total internal energy. Here we consider total moles are these, and FEQ is the equivalent degrees of freedom which can be considered for molecules of mixture. Now this must be equal to the total internal energy calculated by the sum of individual internal energies. So if we write it like F1 by 2 N1 RT plus F2 by 2 N2 RT and so on up to Fn by 2 Nn RT. Just we are using the conservation of energy. Whether you calculate energy independently or mutually, it must be same. But in this expression you can see this RT and 2 gets cancelled out, and on rearranging we'll get the equivalent number of degrees of freedom for a mixture. It will be F1 N1 plus F2 N2 plus and so on up to Fn Nn divided by N1 plus N2 plus up to Nn, that is total number of moles. So this is the expression we use when required for calculation of equivalent number of degrees of freedom for a gaseous mixture. This is quite useful for various analysis as well as numerical problems also. We'll see in different examples later. Just like we have done the conservation of internal energy, we can also analyze the mixing of gases at different temperature using the similar concept. To analyze mixing of gases at different temperatures, say we consider one n gases which are say having degrees of freedom F1, F2 up to Fn, moles which are taken N1, N2 up to Nn, and which are having temperatures T1, T2 up to Tn. Like first gas is having degrees of freedom F1, number of moles N1, and it is at temperature T1. Similarly, these n gases are mixed in a vessel. So if these n gases are mixed, we can state Finally, after mixing, the final equilibrium temperature will change and all the gases will finally be in thermal equilibrium at the equilibrium temperature. If final equilibrium temperature of mixture is Tf, and we also assume that and if vessel is thermally insulated, that means no heat exchange takes place between the gases and the surrounding. These gases are exchanging heat between one another, and finally the equilibrium temperature is Tf. So we can state, as the vessel is thermally insulated, total energy of all gases will remain conserved. So here we can write initial internal energy of all gases will be F1 by 2 N1 RT1 plus F2 by 2 N2 RT2 plus and so on up to Fn by 2 Nn RTn. As all these gases are at different temperature, the sum of internal energies can be given like this, must be equal to the final internal energy or final total energy of all the gas molecules. So for first gas we can write as finally the temperature becomes Tf. It can be written as F1 by 2 N1 RTF plus F2 by 2 N2 RTF plus and so on up to Fn by 2 Nn RTF. So in this situation you can see this 2 and R gets cancelled out for the whole expression, and in this situation directly on rearranging the parameters we'll get the final equilibrium temperature, which is equals to F1 N1 T1 plus F2 N2 T2 plus and so on up to Fn Nn Tn upon this F1 N1 plus F2 N2 plus and so on up to Fn Nn. This is quite a useful and very important expression you need to keep in mind. Always remember the expression as whenever mixing of gases is done in a thermally insulated vessel, the final equilibrium temperature of the mixture can be obtained directly by using this expression.